Hello students and friends. This is part 3 of the lecture series on microelectronics. It emphasizes on a semiconductor device known as transistor. What is a transistor? Literally, transistor means transfer of resistance because it transfers the resistance from one end of the device to the other end. It is a miniature semiconductor that regulates or controls current or voltage, thereby amplifying and generating these electrical signals and acting as a switch or gate for them. So in short, there are two basic functions of a transistor. Number one, it is used to amplify current, and number two, it also blocks the passage of current in a circuit. Before the advent of transistor, it was the vacuum tube that was used with the same function. But a transistor has at least the following advantages over the vacuum tube. Number one, it is smaller in size. Number two, it uses less power. Number three, it has longer lifespan compared to a vacuum tube. So what are the common uses of a transistor? Well, transistors are used, for example, in pacemakers. Also, transistors are used in hearing aids, cameras, calculators, and of course, microphones. There are two basic types of transistors in terms of what uh, eh, what semiconductor materials are used. The first one in our illustration is what we call an NPN transistor. All right. This is the schematic diagram for NPN transistor. You'll notice that there are three layers of the semiconductor material, two N-type materials, okay, represent what we call the emitter and the collector, and the base is the one that is sandwiched between the two uh, N-type materials, right? Whereas for PNP transistors, it's the opposite. The two P-type materials represent the emitter and the collector, while the material that is sandwiched represents the base. It is an N-type. All right, and each also type of transistor has a particular electrical symbol. This is what represents the symbol for an NPN transistor, and that one is for PNP. The only main difference, if you notice, is the direction of the current, all right? The direction of the current between the collector and the emitter, uh, we call it the collector emitter junction. So in NPN transistor, the arrow, all right, is directed towards the emitter. All right, it is as if the charge or charges, okay, are leaving, okay, moving away from the collector, okay, going out into the emitter, whereas the symbol for PNP is that the charge carriers uh, are entering the emitter, all right? So the arrow is going inside and passes through the uh, what we call the emitter collect collector junction until it goes straight to the collector. All right. In terms of size, physical sizes, uh, and it's also emphasized here in the drawing, the N-type material, which represents the collector for an NPN transistor, is bigger in size compared to the emitter. But among the three, it is the base that is the thinnest, right? For PNP transistor, still it is the collector that is bigger, the biggest. It's bigger than the emitter, and the base also is the one that's the thinnest among the three uh, semiconductor materials. All right, and just like diodes, we discussed diodes in our previous episode. Okay, in terms of doping, the amount of impurities that is mixed into a semiconductor material such as silicon or germanium, all right. In the case of NPN transistors, we say that the dominant charge carriers are the electrons, inasmuch as the emitter and the collector are both N-type materials. So electrons are the majority charge carriers. Among the three regions or layers, it is the emitter that is doped heavily, right? Uh, the collector is also doped, but just moderately, and the base is just doped lightly. That's also true in the case of PNP transistors. So it is the emitter that is heavily doped or mixed with uh, an impurity, all right? And then collector, as I said, is moderately doped. Okay? It is the base that is doped lightly, all right? So in operation, we say that the first section, which is the emitter, is the one that supplies the free charges, all right? This for NPN, the charge carriers are the electrons, while for PNP, the charge carriers are the holes. And these are to be collected by the third section or layer, all right, at the opposite end, meaning the collector, okay, passing through the middle section, and the middle electrode represents the base. It is the base, all right, the middle layer, it is the one that controls the current in the collector. Okay, we shall discuss that in the next slide. Also, if you're going to look at an actual transistor, how would you know uh, which among the three electrodes represents the emitter and the collector? Okay, the one in the middle is always the base, so no problem about the base. But which among the three, or which among the two, all right, the left electrode or the rightmost electrode represents the emitter or the collector, all right? This is how you're going to find out. So um, the the transistor itself, has a certain surface that is flat. All right. So you have to uh, position this transistor in such a way that the flat surface is facing you. All right. It is the flat surface that is facing you, and the first electrode to your left is always uh, the the collector. All right. This is the collector. Of course, the one in the middle is the base, and the one on the right is the emitter. So that's always the rule in determining which electrode represents those three layers, whether it is an NPN or a PNP transistor. We now have our first question. Question number one. How should the emitter and collector be connected to their separate voltage sources as shown in the above diagrams? All right. So we have to examine the circuit diagrams carefully. Here are the choices. Letter A. The EB junction. EB means the emitter and the base junction. And the CB or collector base junction are forward biased. For letter B, the EB junction and the CB junction are reverse biased. Letter C, the EB junction is forward biased, while the CB junction is reverse biased. And the last option, the EB junction is reverse biased, while the CB junction is forward biased. All right. So, what do you mean by a forward bias? So, we say that a particular junction, let's look at the first illustration for an NPN transistor, right? You will notice that uh, the N-type or the N-type layer is connected to the negative terminal of a battery, all right? Now, we know that in the N-type material, it is the electrons that act as the charge carriers. So, we say that the EB or the emitter base junction is forward bias. Whereas, all right, uh, the CB, meaning collector base junction, is connected in reverse bias. All right, because N-type is supposed to be the charge carriers are also electrons, but they are connected to the positive terminal. So that is what we mean by reverse bias. All right. Is that different for a PNP transistor? All right. Let's examine. All right. The emitter-base junction, such as here, this one, the charge carriers in the P region, right, in the emitter region, are the holes. And if you notice, they are connected to the positive terminal of the battery. And therefore, we say that the PN junction, I mean the EB junction, okay, emitter base junction is also forward bias. While the uh, collector base junction, since P is the charge carriers in P material are also holes, okay, hence are considered positive, but they are connected to the negative terminal of the battery. So we say that the CB junction are in reverse bias. So it doesn't matter whether you're talking about NPN or PNP, they are both characterized by the same type of biasing. All right, forward bias for the emitter base and reverse bias for the collector base junction. As represented here, V stands for voltage. All right, VF specifically suggests that the battery here is forward bias, while VR represents the voltage, okay, uh, in the CB junction, right? Labeled VR, therefore it is represents reverse bias. You will notice also that between the two batteries, all right, we emphasize that the VR, okay, has greater voltage compared to uh, the first battery. This is the input as far as the circuit is concerned, all right? This is the input voltage, and that is the output voltage, all right? So that's true for NPN and PNP transistors. Therefore, looks like our answer for this question is letter C, all right? Letter C, the emitter-base junction is always forward bias, and the collector-base junction is always in reverse bias. Before we move on to question number 2, we'll first describe uh, what we said earlier, that it is the base that controls the current in the collector region of the transistor. So the transistor is important because a small change in the current flowing from the base to the emitter, we call it the base current, represented by I sub B, right? We call it the base current. This causes a large change in the current flowing from the collector to the emitter. It's called collector current IC, all right? And if you're going to plot the amount of uh, base current, okay, expressed in microampere versus the amount of collector current expressed in milliampere along the y-axis, they are in different units to emphasize that the base current is much smaller compared to the collector current. All right, so this is what happens. The graph almost looks nearly straight, all right, nearly straight line through the origin. This means that the collector current, okay, can be described to be directly proportional to the base current. And in equation form, okay, we have the following equation. We talk about the current that is gained for a kind of amplifier, all right? We call it the um, where the what do you call this? The emitter is held common, all right, or constant, common emitter type of amplifier. We talk about what we call current gain, and that is represented by the Greek letter beta. So beta is just the ratio of the collector current IC to the amount of the base current IB. Okay? This is the result of um, plotting the graph IB, or base current, versus IC, or collector current. Okay, you almost get a straight line graph sloping upward to the right. So if you're going to calculate the current gain, uh, where the emitter uh, is the one that's common, all right, we shall show the diagram, circuit diagram for this kind of an amplifier in our succeeding discussion. All right. All right. Uh, let's discuss further what we mean by a common emitter amplifier. We have here a diagram that shows the circuit of a common emitter uh, setup or diagram. All right. So we say that the emitter is the one that's common. Simply means that the base, all right, if you notice, the base is directly connected to the emitter, all right. So their connection is referred to as the emitter-base junction, all right. And if you notice also that the collector is also directly connected to the emitter. So the emitter is the one that's common, all right. Notice here that the direction of the current IB, all right, the base current, that arrow represents the base current, okay, and it was mentioned that it's the base current that controls the collector current. So in this kind of setup, small amount of base current will produce a large amount of collector current. So IC represents the collector current. Okay, this branch of the circuit normally is what we call the input voltage. So this is the input voltage, and that is the output voltage. Notice that there is an output resistor, all right, connected to the collector emitter junction. And a common emitter amplifier simply means that current is being amplified. Small amount of base current can be amplified to produce a large collector current. That's why we talk about current gain. Okay, the amount of collector current is much higher compared to the amount of the base current. All right. So in computing for that current gain for a common emitter amplifier that is represented by beta, okay, the value of beta, okay, is always greater than 1. All right. In other words, this amount of current that is gained, okay, uh, describes what you mean by uh, current amplifier. One of the functions of a transistor is to amplify the amount of current, and that's precisely what happens in a common emitter amplifier circuit as shown here. All right. So again, uh, earlier we described that the collector, in this case, it's a p-type material. Notice that it is connected to the negative terminal of the battery, so it is in reverse bias. right? Whereas the base emitter junction, all right, whose charge carriers are the electrons. Notice that they are connected to the negative terminal of the battery in the input, all right, battery. So it is forward biased. But the fact that the emitter is the one that's common in these two branches of the circuit, we say that it is a common emitter circuit. So, supposing that the voltage along the input voltage supply is zero, meaning there is no voltage yet here, right? The current IC is very small, all right? So most of the voltage VC appears across the uh, base collector junction. Okay. When the voltage in the input, we label it as B sub B, increases, the base collector potential, all right, decreases. And therefore, more holes can diffuse into the collector. Okay. We're talking about the base collector junction. Okay. So if the amount of voltage in the input is increased, all right, that produces even a small amount of base current, okay, is enough to produce large collector current, right? So ordinarily or normally in this situation, the collector current is much larger than the base current, as emphasized in this equation, where the current gain is much greater than 1. There's another type of amplifier. We call it a common base amplifier. Right? So here is the diagram for a common base amplifier circuit. Right? It's called common base amplifier because if you notice, the emitter and the collector both share the same, what you call, uh, the junction is between the emitter and the base, as well as between the collector and the base. So as shown in the diagram, all right, we have here for our input, all right, the input voltage where the voltage when increased will produce what we call the base current, or the current that is responsible for producing a large collector current, right? So that's precisely what we mean by common base amplifier. But unlike the previous type of amplifier, the common emitter, this time when you talk about the current that is gained, all right, it is the collector current, all right, that is to be divided by the emitter current. Okay, so the emitter current, the one that is produced in the base emitter junction, right, labeled here as I sub E for emitter, right? When I sub C, or collector current, is divided by I sub E, then we talk about the current gain represented by alpha. Okay, take note, alpha is different from beta. This time alpha is the ratio of the collector current over the emitter current. That's why it's called a common base amplifier. What is amplified is not actually the current. So it is the voltage that is amplified. All right. For example, when the um, emitter voltage labeled here as V sub E, that's when the input is equal to 0, all right, that means there is no current. There may be, but it's very small, all right. When the potential across this input, okay, voltage V is applied between the emitter and the base, the holes now will travel from the emitter, all right, to the base. Why holes? Because we are talking about a PNP type of transistor. So the majority charge carriers are in fact the holes. So when VE is substantially increased, okay, between the emitter and the base, then the holes travel from the emitter to the base. That therefore, what there is what we call an emitter current that arises. Okay, when VC, the one in the output branch, VC, meaning collector voltage, is sufficiently large, most of the holes continue into the collector. Okay, that's how the collector current arises. All right, for large output voltage VC, okay, uh, the collector current is also large, but that current IC is controlled not by the collector or not by the base current, but by the emitter uh, current in the circuit. So that's different from what we discussed earlier, right? In the common emitter circuit or amplifier, it is the base current that controls the collector current. But this time, in a common base amplifier, it is the emitter current, right? I sub E, that controls the collector current. That's why for a common base amplifier, the current gain alpha is equal to IC over IE. All right, and this value for alpha, unlike in the case of beta, alpha is always less than 1. Right. So we now have question number 2. Which of the following statements is or are considered correct or true? Okay, there are one or more answers. Letter A. Collector current IC is slightly smaller than the emitter current IE. Letter B. IC is slightly greater than I sub E. Letter C. Base current IB is much smaller than the emitter current IE. And letter D. IB is much greater than IE. Right. So our answer, we first say that when the majority carriers due to forward biasing of emitter-base junction are repelled by the repulsive force from the battery and move over to the base region, uh, an emitter current IE arises. Okay, since the base is thin and lightly doped, all right, only few majority carriers of the emitter are neutralized at the base, hence base current is low. Okay, the remaining majority carriers of the emitter are able to pass to the collector, hence collector current IC arises. We therefore say that among the three, I sub E is the largest, all right, because it is just equal to the sum of the base current IB and the collector current IC. So based on this analysis and equation, our best answer for this question is letter C, that the base current is much smaller than the emitter current. And that's also true for letter A. There are two possible correct answers. The collector current is slightly smaller than the emitter current, okay, as shown in this equation. IC is slightly smaller than I sub E, but base current IB is much smaller than I sub E, right? Letter B is incorrect, as well as letter D. Question number 3. Letter A. In a PNP transistor, how much emitter current I sub E with 100 milliampere for collector current IC and 800 microampere for IB? Question letter B. What is the current gain for this common base amplifier? Alright. So our formula for finding IE is IE equals IC plus IB. Then, since IC is 100 milliamperes and the base current 800 microampere, when converted to milliampere, that's 0.8 milliamperes for a total of 100.8 milliamperes as the value of the emitter current. So that is the answer to letter A. For letter B, we are asked to find the current gain for this common base amplifier. So we are talking about the current gain alpha, whose formula is IC divided by IE. And substituting, we have 100 milliamperes for IC divided by 100.8 milliamperes for I sub E. And therefore, the current gain alpha is equal to 0.99. And as earlier emphasized, alpha is always less than 1. In this example, it is nearly equal to 1, 0.99. Question number 4. In case of common emitter transistor amplifier, the ratio of the collector current to the emitter current is 0.96. Question. What is the current gain of the amplifier? Is it letter A 6, letter B 12, letter C 24, or letter D 48? So for our solution, the ratio of the collector current to the emitter current is given as 0.96. So that means if we transpose this equation, we have IC being equal to 0.96 multiplied by IE. All right. And we also have the formula for finding IE, which is the base current plus the collector current. Okay, and that would mean, since we already expressed IC as 0.96 IE, we just substitute that here. So IE becomes equal to IB plus 0.96 IE. And we will have the formula to find the base current. That means transposing point of 0.96 IE to the left side of the equation gives us IB being equal to 0.04 IE. And using the formula for the current gain beta, all right, because it is the emitter that's common, where beta is equal to the ratio of IC over IB. All right, and we already have the expression for IC. It's 0.96 multiplied by the emitter current. Okay, divide that by the base current in terms of the emitter current, that is 0.04 IE. That cancels, all right, the collector current IE, and our value for beta, therefore, is equal to 24. So that is the current gain of this amplifier. As expected, beta is much greater than 1. Before we proceed to our next question, let's first talk about uh, an example of transistor that is used as a switch. One of the functions of a transistor is it acts like a switch. So the transistor can be used as an electronic switch, okay, as shown in this circuit diagram below. The emitter is at the potential of 0 volt. By the way, this kind of circuit is based on how you're going to connect all these components in a what they call breadboard. All right. So breadboard physically somewhat looks like this. Okay. So if the potential of the base is less than 0.6 volts, no base current flows. All right. No collector current flows, and the switch is off. Right. If the potential of the base rises above 0.6 volts, then a base current flows. There is now a large collector current and the switch is on. So basically, as you can see in the diagram, all right, we have a resistor R1 amounting to 100 kilo ohms. And then there's a variable resistor R2. That symbol represents a variable resistor, meaning you can vary the amount of resistance in this resistor. Say, for example, you begin at 0 resistance, then you can increase it, all right, to as much as uh, the amount of what R1 has, 100 kilo ohms. All right, so again, there is another resistor. This is for safety purposes. That is in series to the base, all right, to the base um, of a transistor. Okay, so it says here that there is no voltage in the emitter. Okay, 0 volt. That means if the potential of the base is less than 0.6 volt, there will be no base current. All right, such amount of voltage, in other words, the limit, if the potential, the base is less than 0.6 volt, all right, then there will be no substantial amount of base current that will flow. And that amount of current flowing into the base, okay, can be controlled, in other words, okay, by this variable resistor. If variable resistor R2 is 0, that means obviously the current, okay, that goes from the positive terminal of the battery, right, will just go straight to the uh, negative terminal. When you say 0 volt terminal, that's understood to be the negative terminal. Since there's no resistance here in this component, okay, current will not go through the transistor, so it just goes straight. In other words, the current here at point X is 0, so there will be no base current. But if you're going to slowly increase the what you call the variable resistor, okay, such that what happens is the voltage is now divided. All right, the 6-volt input is now divided between these two resistors. All right, there will now be a certain amount of resistance R2, okay, that will make or that will produce, okay, substantial amount of base current along point X. That means the current now is able to what you call pass through just a small amount of base current is enough. All right, it's enough to cause a bigger collector current, which the collector current is the output. All right, that is what will enable this light bulb to glow. That means if the light bulb glows, it means that the transistor has acted as a switch. Okay, it switches on this light bulb. But earlier, when the resistance R2 is 0, okay, the transistor will act as also as a switch, but it switches off, all right, the bulb. All right, so this is how the transistor acts as a switch. We're down to our last question, question number 5. An automatic light switch uses a light-dependent resistor, or LDR, whose intensity is inversely proportional to the resistance. This is to switch the transistor on. So your task is to fill in the missing words. But before we look at the paragraph, let's first analyze our circuit diagram. Alright, so this is a diagram that illustrates how the components, alright, such as the LDR, we have here a resistor load R1 equal to 10.0 kilo ohms, and there's also another resistor for safety purposes, 22 kilo ohms. This is in series to the base, all right, of a transistor. BFY51 is the most commonly used type of it's a bipolar type of transistor. This is made of silicon, and as shown by the symbol, it is an NPN, okay, resistor, whose collector, as you can see, is connected to the positive terminal of a battery, all right, passing through a load. The load is a lamp whose voltage capacity is 6 volts or 60 milliamperes, all right. So the emitter, this is the emitter, all right. The emitter is what we call forward bias, okay. This terminal 0 volt is understood to be a negative, all right, terminal of the battery. So since this is negative, and an NPN transistor like this, okay, would mean that the emitter is connected in forward bias, while the collector, right, is connected in reverse bias. So here is the uh, light dependent resistor. All right, this is the electrical symbol for an LDR. All right, so its its resistance is dependent on the intensity of the light. that strikes the LDR. And as pointed out in the question, the resistance is inversely proportional to the intensity, which means that uh, the higher the amount of light, okay, the less is the resistance of this resistor. And the lower the light, meaning if the surrounding is quite dark, meaning we have a dim light, that is the time when the LDR would have, okay, a higher resistance. All right. So we will now look at the paragraph that describes this circuit, and all you have to do is fill in the missing words in the blanks. Here's the first part of the paragraph. When the intensity or when the light intensity is blank, number one question, the resistance of the LDR is low. Okay? The potential of the base is lower than or is below the 0.6 volt needed to switch the transistor on. As the light intensity falls or drops, the resistance of the LDR blank, all right, that is uh, the second answer. The potential of the base rises above 0.6 volt, and so therefore a blank current, for number 3, a blank current flows. This allows a much bigger, for number 4, bigger blank current to flow and light the blank. Alright, this is the first part. We'll see the second part in the next slide. For the second part of the paragraph, you will be referring now to the circuit diagram as shown below. We have replaced the LDR with a variable resistor. So it's now a variable resistor that is connected. Alright. And as shown, the other components are intact except for the resistor number 1, whose amount is now changed to 100 kilo ohms. Alright, so here is the continuation of the paragraph. The transistor can be made to switch at different light intensities by altering the blank, that's entry number 6. If blank number 7 is set at 0 resistance, point X is at 0 volt. No base current flows and the switch is blank. As R2, meaning the variable resistor, is increased to blank kilo ohms, the 6 volt is shared across the two resistors. When the potential at point X rises above blank, alright, that's entry number 10, a base current flows. This allows a collector current to flow and light the lamp. Okay, so uh, I'll be revealing the answers for the two paragraphs in 3 minutes. Alright, so I think it's 3 minutes is up. I will now reveal the answers for the first part of the questions. Here they are. Alright, so let's go over. First entry is number 1. When the light intensity is high, the resistance of the LDR is low. Alright, we mentioned that the light intensity is high because the relationship between intensity of light and the resistance of the LDR is inverse. And therefore, if the resistance of the LDR becomes lower, then that means the light intensity is high. Okay, the potential of the base is below zero point 0.6 volts needed to switch the transistor on. As the light intensity falls, the resistance of the LDR, all right, blank. So the correct answer for number 2 is rises or increases. All right. Uh, at low intensity, the resistance of the LDR should be high. That's why our answer for number 2 is rises or increases. Okay. The potential of the base rises above 0 0.6 volts. All right. So for number 3, a blank current flows. Correct answer therefore is a base current flows. All right. This allows a much bigger blank current to flow. So for number 4, that refers to collector current. Remember the relationship between the base current and the collector current. All right. And the light, the blank. For number 5, it is the bulb or the lamp. So you can also have lamp as your answer instead of bulb. All right, so these are the complete answers for the first part. We'll proceed to the second part. So the answers for the second paragraph, these are the answers. All right, so let's go over. The transistor can be made to switch at different light intensities by altering the variable resistor R2. If, number 7, if R2 is set at 0 resistance, point X is at 0 volts, and no base current flows, so the switch is, number 8, the switch is off. As R2 is increased to blank kilo ohms, entry number 9, that should be 100 kilo ohms, alright? For the two resistors R1 and R2 to be sharing the voltage of 6 volts equally shared, therefore R2 should be increased to the same voltage, the same resistance as R1, that is 100 kilo ohms. When the potential at point X rises above, all right, mentioned several times, above 0 0.6 volts, a base current flows, and this allows a collector current to flow and light the lamp. So that's it. We're done answering question number 5, and also that ends our video tutorial for this lesson. Thank you very much as usual.